we usually use a unit circle or triangles, which is what we're going to do today, to evaluate trigonometric functions. Well, those are for nice values, for the reference angles that we know that are 30-degree, 45-degree, or 60-degree angle. And of course, there are multiples and their corresponding locations in the different quadrants, right? So just make sure to put the correct angle. However, in applications, which is part of what we're going to do today, if not today, maybe next time, we may need to evaluate cosine, like cosine of 15 degrees. Well, if we do cosine of 50 degrees, I believe that's pi over 12, because pi over 6 is 30 degree. Half of it, which is 15 degrees, that has to be pi over 12, which we have it in radian here. Well, in this case, we don't have nice order pairs, nice values like the ones that we have for 30, 45, and 60 degree angles. So what do we do in this case? Well, we use a graphing calculator. Don't get me wrong, we're going to get to evaluate cosines and sines of 15 degrees, pi over 12, pi over x later in the semester when we look at, what's this, formulas for the addition of angles and the double angles, the half angle formulas. Well, but those are not going to be there in the unit circle. Well, but you'll see how we're going to get those. In the meantime, let's use our graphing calculator to calculate these results. And well, you need to be very careful. There's a couple of caveats here. Number one, our graphing calculator it's only able to it's only able to compute sine, cosine, and tangent. So the secant, the cosecant, and the cotangent functions are not in the graphing calculator. However, check this out. Check how we know the reciprocal functions for cosecant, which is 1 over sine, the secant, which is 1 over cosine, and the cotangent, which is essentially 1 over tangent theta. All right? Well, what is this going to mean? Oh no, my laptop is dying. What is that going to mean in the end? Well, so we will have to use reciprocal functions to, shoot. It's right here. Okay. So we'll need to use reciprocal functions to get these calculations done. All right. So, well, in the meantime, that's one of the caveats here. The other one is that we need to make sure that we are using the graphing calculator in the correct mode. Again, keep in mind that this angle 15 degrees, this one is in degree mode. And all we do, go to the graphing calculator, click on mode, and make sure you're highlighting the degree mode. All right, click enter, second quit, and let's evaluate, what was that? Cosine of 15 degrees, cosine of 15. And final answer, 0.9659. How many decimals? 2 decimal places, 0.97. 0.97. As easy as that. However, yes, be careful. Be careful, number one, with the function you're evaluating, and also be careful that your graphing calculator is set in the correct mode. All right, careful, because what do we have? Sine of 15. Sine of 15. Sometimes we are in a hurry and we just write numbers and symbols. However, when it comes to angles, the notation matters, because this little symbol, this little circle here, means degrees. Whenever you don't see that degree symbol, that means here we are in radian mode. Radian mode. All right, so let's go about. Okay, what's that going to be this time? That's going to be sine this time. Sine of 15. Let me close parentheses. I'm not going to click enter yet because my calculator right here is set in degree mode. I need to go mode, set it to radian, click enter, second quit, and click enter to compute the value. That's 0.65 rounded to 2 decimal places. It's simply 0.65. And that's it. That's about it. All right. Let's verify that indeed these two results are the same when we go about the wrong mode. So degree, second quit, and see how we get two different results. 0.26 rounded to 2 decimal places when the calculator is in degree mode as opposed to the graphing calculator being set in radian mode. So need to be careful with that. What's next? Tangent of pi over 12. Okay, do you see the degree symbol? So this has to be in radian mode. Radian mode. All right, so that means that's tangent. Well, first, let me go mode, radian, and second quit. Click on tangent of second pi over 12. Close parentheses, click enter, 0.2679, well, that's 0.27. So this is 0.27. No work needed to be shown in this case because it's a calculator type of question, right? It's again, just make sure you're in the right mode. Now, secant of 10. Well, number one, we don't see the degree symbol. That means we are still in radian mode. And well, the secant function is not in the calculator's catalog. That means we need to use a trigonometric identity, namely 1 over cosine of 10 radians. And let's compute this via the identity, the reciprocal identity. That is 1 over cosine. Was that a 20? No, 10. 1 over cosine of 10, close parentheses, and click enter. Negative 1.19. All right. Because rounded to 2 decimal places, the third digit is a 1. It's not big enough to round it to 2 zeros. So negative 1.91. Final answer. And I believe this is the end of the section. That's about it for 4.2. So today we're going to move on to section 4.3. You will realize that we are going to be doing essentially the same thing. However, what we're going to do in the next section, even though it's the same, it's obtaining the same values of the trigonometric functions, this time we're going to take a right triangle approach, not a unit circle approach. Well, first of all, let's do a connection between the circle approach and the triangle approach, and I believe I already covered a little bit of it because, well, check this out. So these are all these points that lie on a circle, not necessarily a unit circle, but could be a unit circle or a circle of any other radii. Let me draw a circle, a full circle here. So if we choose a point on the circle here, well, if we go from the origin to any point on the circle here, check this out. This point will have a projection in the x direction and a projection in the y direction. That means we need to move a unit in the x direction and b units in the y direction. This will create a right triangle project or inscribed inside of this circle. And again, we are assuming that the circle is in standard form, in standard position. That is, it has its center at the origin and whatever radius that can be. Not necessarily the unit circle, because this hypotenuse of the triangle here, which is essentially the same as the value of r of the radius, we will see how it is in some situations, in most situations actually, is not going to be just the value of r equals to 1. Not anymore. Now we're going to define the right triangle trigonometry, most commonly known as SOHCAHTOA. All right, and that's something you may have seen before. So number one, before defining the trigonometric functions, we need to set a reference angle. That's very important because from that reference triangle, we are going to determine the opposite side, the adjacent side, and the hypotenuse. However, if you change the reference angle, and let's say alpha here, these are no longer opposite and adjacent. Now the B is the adjacent and A is the opposite. So we need to be very careful when choosing the reference angle because that's actually that's the primary reference, the basis here, if we will. All right. So number one, we define the sine function to be the opposite over hypotenuse, in this case B over C. Cosine, which is adjacent over hypotenuse, A over C. And tangent, which is B over A, that is opposite over adjacent. From here, check this out. Here is where the SOHCAHTOA acronym is coming from. That's let me highlight the letters. SOH, that's the SO, and then CAH, that's the CA, and then TOA, that's the TOA. So if you ever wonder where was that SOHCAHTOA coming from, that's where. That's to say, sine equals opposite over hypotenuse, cosine equals adjacent over hypotenuse, and tangent equals opposite over adjacent. And of course, from there you can derive the other three trigonometric functions by just finding the reciprocals. That'll be Cho, Sha, Kao, I guess. But you don't need the Cho, Sha, Kao. The SOHCAHTOA is more than enough. All right? From there you can get pretty much everything else. Let's do one example using SOHCAHTOA. So they're asking us to find the value of the 6 trigonometric functions for the angle theta from the figure below. And again, the position of the reference angle is very, very important. Right now, in this case, we are given the adjacent side and the hypotenuse. And well, notice the opposite side, the side that it's facing against the reference angle, it's not given. It's just labeled as opposite. Well, we need to figure out the length of that side in order to find the 6 trigonometric functions. Any ideas on how to find the missing side? Pythagorean theorem, right? Pythagorean theorem, that's how. So that's a squared plus b squared equals c squared. That means a squared, which is 3 squared, plus b squared, that's let's call the opposite side to be b, we don't know what it is, equals to 5 squared. That's let me go up here. That's a 9 plus b squared equals 25. B squared equals 25 minus 9, which I believe is that a 16. And b equals, okay, I know what you might be thinking here. And yes, we are right. That's supposed to be a plus or minus the square root of 16, because that's how the square root property works when solving these kind of baby quadratic equations. However, well, I'm going to skip the plus minus in this case, because here we're solving a quadratic equation in the geometric context. And in this case, there's no such thing as negative lengths of on a rectangle or any geometric shape. So I'm just going to go with the positive, which is 4. So we got it. That's 4. All right, let's do SOHCAHTOA. Sine theta, that is the opposite over the hypotenuse. Well, the opposite side whose length equals to 4 divided by the hypotenuse, which equals to 5. That's it. Let's find out what cosine is. So cosine theta, which in this case by definition adjacent over hypotenuse, that equals to 3 divided by 5. And tangent, which is opposite over adjacent, that equals the opposite, which is 4, over the adjacent, which is 3. All right? For this simple case, I mean, if you want to go with the definition for sine whose reciprocal would be the cosecant function, that should be only hypotenuse over opposite. Secant would be hypotenuse over adjacent, and tangent adjacent over opposite, or just find the reciprocals. It's the same idea from before. As far as the trigonometric identities go, it's the same definition, same ideas. It's now a different point of view this time. Instead of using a unit circle or a circle of radius r, whatever radius can be, we're going to use just triangles this time. So from here we can get cosecant, from here we can get secant, and from here we can get cotangent. Just find the reciprocals of each. And that's about it. Just that. All right. Let's see what's next. Questions about this? I guess this is pretty straightforward, from formulas, from definitions, and just connect those definitions with their corresponding values that we use to get the corresponding values of the trigonometric functions. And again, no more circles, just triangles. However, well, I guess we're going to bring up the circles a little bit later, just so we can see where the values for the trig functions will come from. All right. Okay, so let's do another presentation for this kind of problems. I mean, you will find out how in this case it will be the same type of process, the same calculations. But it's just a presentation of how we're given this. All right. Suppose that cosine theta equals square root of 5 over 3 for the acute angle theta. Evaluate tangent theta. All right. Number one, by the SOHCAHTOA definition, when we have the cosine function, this is the adjacent, and the numerator is the adjacent, and the denominator will be the hypotenuse. I was going to say the opposite, no, but it's the hypotenuse. So how about we draw a right triangle representing this angle with the corresponding sides. So, and well, this is our reference triangle. You can position the triangle and the angle at your favorite position. That's fine, as long as you keep the idea for opposite and adjacent. That's good enough. But preferably we draw a triangle in this direction, like if it were in the first quadrant, if we were to impose a Cartesian plane and have the angle to be the acute angle as a reference. So, but I mean, you can do it here as well, but I wouldn't recommend. I would recommend, my advice is to do it this way instead. But if it works for you to do it in a different way, that's fine. All right. So they're telling us that the adjacent side, it's the square root of 5 units, and the hypotenuse is 3 units. And again, we're missing the length of the opposite side. We're going to use the Pythagorean theorem to find that length of the missing side. That is, a squared plus b squared equals to c squared, where how about the given side is a, the missing side is b, and c is the hypotenuse. That's fine. That'll be then the square root of 5 quantity squared, and careful with this calculation, plus b squared equals to c squared, which is 3 squared. All right, so we just set up the Pythagorean theorem problem for this triangle setup. Now, check this out. The square will cancel the radical here, giving us a 5, leaving us with a 5 plus b squared, and 3 squared equals to, oh, I did a cube here, it's supposed to be squared, all right? So that's a 9. Now, solving for b squared, we get b squared equals to, okay, subtract 5 on both sides to get 4, and b equals to 2. That's the square root of 2. I know there is a square root involved, and there is a potential, what's that, plus minus, but again, in the geometric context, in the context of geometry here, we know we're no longer considering negative length, right? So that equals to 2. So we're ready to evaluate tangent of this function. Tangent theta equals, well, in this case, notice they're not asking us to evaluate the 6 trigonometric functions, only the tangent function. And tangent theta, which by definition is opposite over adjacent, that equals to the opposite, which is 2 units, and the adjacent, which is the square root of 5. And we're essentially done with finding tangent given this triangular setting. However, again, Alex may not like radicals in the denominator, so the only thing you might want to do is go the extra mile here and multiply numerator and denominator by root of 5 to rationalize the denominator. And that's going to be then 2 square root of 5 divided by the square root of 5 squared, which is in this case simply 2 root of 5 over 5. Sounds good? Okay, let's see what's next. Let's see, trigonometric functions for special angles and identities. So it's mostly identities, but one thing I would like to mention here. I'm not going to go over all of the identities again. Those identities that we already know, which are the reciprocals, the quotient, and the Pythagorean identities, because those we already cover them. So I guess at this point we're already familiar with those. We are already familiar with the fact that secant is the reciprocal of cosine, cosecant is the reciprocal of sine, and cotangent is the reciprocal of tangent. So we're going to learn a few new identities that we're going to call the cofunction identities, and that's to define the relation between sine and cosine pairwise, tangent and cotangent pairwise, and secant and cosecant pairwise. All right, we'll see about it. In the meantime, well, before we get there, how about we redefine the nice values that we had from the unit circle? That is, what do I mean by nice values? Nice values are the trigonometric values for the order pairs on the unit circle corresponding to the 60-degree angle or pi over 3, the 30-degree angle or pi over 6, and 45-degree angle or pi over 4. All right? Now, again, this point to go from the origin, because again we are centering this circle at the origin. That is, we have a standard circle, and it turns out we also have a unit circle, by the way. So to go from the origin to that point on the circle, we need to move x units in some units in the x direction and some units in the y direction, and the distance between that origin and the point on the unit circle, it turns out that it forms a right triangle. All right, and well, those components for the point 1/2 and root of 3 for the 60-degree angle, that again, just to review, this is the cosine function, and this is the sine function. Again, these are order pairs, so they go in order. The x component is cosine, the y component is sine. But again, if we were to go through the right triangle point of view, this 1/2, which is the x, that's the number of units, the length of the adjacent side for 60 degrees, and this root of 3 over 2 is the length of the opposite side to the 60-degree angle. Right? Same for the 45-degree triangle. Well, we have x and y actually to be the same, root of 2 over 2. Root of 2 over 2 for y, root of 2 over 2 for x. And well, for what else? For the 30-degree angle, well, that's actually the components interchange in comparison with the 60-degree angle. All right? And well, nothing is going to change about it. Well, so we're going to use this idea or this, I think this is a good way to summarize all the values. And then from here, just move it, for example, to another, let's say, what angle is this? Is this 180 plus 45? Is that 215? No. 225? 225 degrees, that 180 plus 35? 215, right? So what if you want to find sine of 215 degrees? Or 5 pi over 4? Well, just bring down this length right here, make this a negative root of 2 over 2, and make this a negative root of 2 over 2. That's all we do, depending on what quadrant do we go. What if we want a 60-degree or a 30-degree angle in the fourth quadrant, which would represent, I believe this is 330 degrees, or what's that, 11 pi over 6, all right? Well, this y would be negative 1/2, and this x will still remain root of 3 over 2. So I guess, well, this is my favorite point of view. This is my preferred point of view when it comes to finding or evaluating values of trigonometric functions. But again, if you still prefer the unit circle, you like the unit circle, you found ways to memorize, to fill in the blanks. Well, actually on the exam you were given the entire unit circle, right? I didn't want to say, even though I knew from before, I didn't want to spoil that part. But ultimately, what matters is to understand how to use it, right? Well, that's one point of view. If you like that, that's fine. If you prefer triangles, that's fine as well. Just as long as you get the correct results, that's what matters in the end. So let's evaluate tangent of 60 degrees minus tangent of 30 degrees. All right. So where are we at? Okay, let me erase all this so I don't, it's recorded anyway, but I need to clean this up to when I refer to this. All right. Tangent of 60 degrees minus tangent of 30 degrees. Now, first of all, tangent of 60 degrees, which is, okay, let me go to the 60-degree angle, and tangent is opposite over hypotenuse. That, isn't that the same as y over x from the unit circle? Essentially nothing changes. All we're doing here is just stamping a triangle. That's all it is. That's all it is. And well, tangent of 60 degrees, which is y root of 3 over 2 over 1/2, minus tangent of 30 degrees, which is 1/2 over the square root of 3 over 2. Well, number one, when we divide fraction by fractions, let's multiply by the reciprocals of those fractions in each case. That is, root of 3 over 2 times 2 over 1 minus 1/2 times 2 over root of 3. Well, check what's going to happen. So that's cancel the 2's, cancel the 2's. That's going to leave us with the following. I'm going to write down this root of 3 over 1. I'm going to leave a space. You'll see why. I think you can see why am I doing this. And that's because, well, we have a couple of fractions with different denominators, by the way. So we need to find a least common denominator, that is multiply the first fraction by missing factors so that we get the same denominator. And that's multiplying and dividing by square root of 3. Well, in the numerator of the first fraction, we get square root of 3 times itself. Get rid of the radical, just write whatever remains inside, that's 3 over root of 3 minus 1 over root of 3. And this will be equal to 3 minus 1 over the square root of 3, because now we have a common denominator. We can combine the fractions together. Let's just do the indicated operation between the two terms, which in this case is a difference. In other words, 3 minus 1 equals to 2 over root of 3. But again, radicals in the denominator.
Multiply, divide by root of 3 to get 2 root of 3 over 3. Final answer. Alright.
We're going to use the same picture from above to evaluate this quantity. However, well, the initial picture, which by the way I got from the textbook, doesn't have the angles in radians. That's what I did here to write them down for you so we can refer to them when doing these calculations. Well, so they're asking us to find the quantity 2 sine of pi over 6 cosine pi over 6. So there's two quantities that we need to find out what they are first. Number one. So sine pi over 6 and cosine of cosine of pi over 6. All right, what's this going to be? Number one, let's go to the pi over 6 triangle in this case, and sine happens to be 1/2 over 1 because the sine function is opposite over hypotenuse, that is 1/2 or 2 times. First of all, 2 times 1/2 over 1 times the cosine quantity, which is the adjacent, which is root of 3 over 2, divided by the value for the hypotenuse, which is also 1. That's root of 3 over 2 over 1. Well, the division by 1, it's kind of useless, if we will. I mean, there's nothing interesting to do about it. That's 2 times 1/2 times root of 3 over 2. And well, notice this is 2 is the same as 2 over 1, and check how we can divide out the 2's, and final answer, root of 3 over 2. All right. Well, I know it looks like certain redundancies are going on here because we are obtaining the same values as in the previous section. The notation of the exercises, they look the same. They don't look any different if you ask me. It's just, again, the point of view of how we get those values. This time by inscribing triangles as opposed to use the values from the unit circle, which again, they're exactly the same. All right. As far as the new identities that we're going to learn, these are the co-function identities. And well, the idea here, first of all, is that, check this out, co-functions of complementary angles are equal. What's that? Well, if we see this identity here, we can see, okay, actually this is, need to be careful because this looks like 2 together looks like multiplication. No, there's no multiplication here. I know, this one right here looks like a multiplication, but it's not a multiplication. It's just the space in between the formulas is not, let me put a comma so you don't confuse them with a multiplication, okay? Alright, so what you're trying to say is that sine of theta equals cosine of 90 degrees minus theta. Well, how is that related with complementaries and co-functions? Well, think about complementary angles. Remember how complementary angles are 2 or more angles whose addition equals to 90 degrees? Just like supplementary angles are 2 or more angles whose addition is 180 degrees. Well, in this case, we want the complementary angle. So, in the same way that sine theta equals cosine of 90 degrees minus the given angle, that is the complement. So, that is the difference between 90 and the angle, it's going to be the complement. Well, we're given the version in degrees and we're given the version in radians. Tangent is complementary to cotangent of 90 degrees, and the same cotangent is complementary to tangent of 90 degrees minus theta. Well, it looks like a lot of formulas to like write down or memorize, but I mean, there is one thing that you need to keep in mind. Check this out. Okay. On the one hand,
cosine equals complementary sine. Complementary sine. That's what cosine means. It's a sine, but complementary. In the same way that, what else? What's the next function? Um, cotangent equals complementary tangent. All right, and likewise, cosecant is the complementary secant. That's what the co-functions are. That co-prefix means complementary, and that's because they are the same function when we shift them 90 degrees. All right, so how about we see this graphically? I know we haven't looked at the graphs of the trigonometric function, so let's do the following. Wait, let me do, oh no, I'm going to remain in radian mode. So let me clean this up. So I'm going to write down sine theta, or sine x, and at the same time I'm going to write cosine of secant pi over 2 minus x, minus theta, which in this case represented by x. All right, let me graph these two functions. Notice how they are the same graph. They're overlapping graphs because cosine is the complement of the sine when shifted 90 degrees. Well, complementary angles, the difference between the angle from 90 degrees. All right, let's see how can we apply these co-functions together. Well, we're given the cosine of an angle, but they're also giving us the result. They're not asking us to calculate or to evaluate the function. What they're asking us here is to use a co-function with the same value. Number one, let's first of all find. Okay, let's identify the function that we want to evaluate. That is, in this case, cotangent. So that is, its complementary function will be tangent. That is, tangent of. We will find out what this is. Let's figure out the complement. Well, so the complement of 15 degrees, it's going to be, let me call it C, equals to 90 degrees minus 15 degrees, which results into, what's that, 75? 75 degrees, all right? So that's what we want to do, 75 degrees, tangent of 75 degrees equals to 2 plus root of 3, all right? What are we doing? Two things here. Identify the complementary function because cotangent is a complement of tangent, and we also find the complementary angle for which we want to evaluate, all right? And these two have to be the same quantity here. All right. Let's see. Let's do this on the graphing calculator to verify our results because, I mean, you can just write this down and just believe in me. Well, let's just do it in the graphing calculator. Number one, well, I don't know what 2 plus root of 3 is. So let's go ahead and evaluate that. 2 plus secant square root of 3. And click enter. It's going to give us a decimal value. All right. And well, notice our calculation here was performed in, or rather, the angle is given in degree mode. So I'm going to set my calculator to degree mode, degree, click enter, second quit, and I'm going to compute these two quantities. cotangent of 15 and tangent of 75. So tangent of 75 first. I'm going to do that one first. Do you see how I get the same result? And well, again, careful, because cotangent is not in the catalog of our trigonometric functions here on our graphing calculator. So I have to go like 1 divided by tangent, because that's the cotangent function, and in this case 15 degrees. Same, right? Same result. So what do? Find a complementary function and at the same time find the complementary angle of what is given. Let's look at the next example and see what we get. For cosine of pi over 6, well, I mean, we know that cosine of pi over 6 is root of 3 over 2. That's the x component for the 30-degree angle for the right triangle, right? Well, so we want to find a cofunction. Well, it turns out the cosine is a cofunction of sine. Now, we need to figure out the angle here inside of the parentheses. Well, so I'm going to go the same way we did over here, the complementary right? The complement of, what's that? Pi over 6 is, well, let me call it C. Well, I'm going to subtract this angle from 90 degrees, but well, check this out. We don't have this in degrees, this time we have it in radians, and 90 degrees in radians is the same as saying pi over 2. No wonder we are given these formulas not only in the degree format, which is 90 degrees, but they're also giving us these formulas in the radian format, so we can refer to one way or another. But I mean, I guess it's not too hard to remember that 90 degrees is the same as pi over 2 radians, right? So, but still, I'm checking in back and forth so we can see this. Well, oh, I'm going to leave some space here for missing factors. You know what we're going to do here, right? Because we cannot add while we have these denominators 2 and 6. We need to find the same denominator. That's times 3 times 3. And that's, what's that? 3 pi minus pi over 6. That's 2 pi over 6, which equals to pi over 3. And well, that's the quantity I'm going to write down over here. And sine of pi over 3, okay, let's verify that. Interesting. Is this the same value? Is sine of pi over 3 the same as cosine of pi over 6, which is root of 3 over 2? Well, in this case, I'm not going to do it in the graphing calculator the same way I did for letter A, because for letter A, I didn't have a reference point on the unit circle for the angle of 15 degrees, the same we have for 30 and 60 degrees. So in this case, let me go back to the triangles and the points on the unit circle from the previous page. All right. So again, what was that again? Forget. Cosine pi over 6. Okay, pi over 6 is cosine of pi over 6, root of 3 over 2, the same as sine of pi over 3? It is, right? Cofunctions, complementary functions, find the complementary of the angle, and we'd better get the same result. All right?